Section 2.4 is about operations with functions. We've been exploring what a function is, we looked at some graphs of some basic functions, and last section we even looked at how we could transform functions. So we are going to start by letting f and g be functions. Let f of x and g of x be functions. Again, this means if they are functions that each input has exactly one output. Okay, again, operations with functions, the whole point is for us to create new functions. So if we had something that showed up, f plus g of x my claim is that this is the same as looking at the function f of x and adding it to the function g of x. We can also look at functions where we had something like the quantity f minus g of x. And my claim here is that this is equal to the function f of x minus the function g of x. Likewise, if we wanted to look at the function f times g of x, and I'm going to use a star to represent multiplication here, just to avoid any confusion, that this is equal to the function f of x times the function g of x. And last but not least, we can look at the function f divided by g of x and that this is equal to the function f of x divided by g of x under the condition that g of x is not equal to 0. And the reason that g cannot be 0 is because we'd be dividing by 0, and that's undefined. We know that we cannot divide by 0, so we want to avoid that. So I want us to look at a couple different functions. I want us to let h of x equal x squared plus 1, and j of x is equal to 3x. I would like us to find h plus j of 5. In order to do this, we are going to think about what is h of 5 and add it to whatever j of 5 happens to be. So in this case, in order to find h of 5, we will plug in 5 and square it and add 1. And j of 5 looks at 3 and multiplies it by 5. So here we'd have 26 plus 15 for a total of 41. H plus j of 5 is equal to 41. If we continue to look at these two functions, h and j, I would like us to find, and I'm going to write this in blue, I would like us to find h times j of 2. So here we're going to find the value of h of 2 and multiply it by the value of j of 2. H evaluated at 2. We'd take 2 squared plus 1, so that should be 5. J evaluated at 2. 3 times 2 is 6. So when we look at 5 times 6, we get 30. That means h times j of 2 is equal to 30. And then the last one that I want us to look at is I want us to look at j minus h of x. So this should be j of x minus h of x. And here, if we look at j of x, the function evaluated at x gives us 3x, and we are going to subtract off. I always put, when I'm subtracting, whatever it is in parentheses. This will guarantee that I distribute the negative in the correct way. So you can see when we subtract off the function h, which is x squared plus 1, that we will have to distribute our negative. And when we distribute our negative, we're looking at 3x minus x squared minus 1. And just rearranging terms so the x squared is first. That's x squared plus 3x minus 1. That would be j minus h of x. Now I'd like for us to look at some other functions. So we'll call one of them f of x. And we'll say f of x is equal to the square root of x. And g of x, our function g of x, we'll say is equal to x. So I would like for you guys to take a moment and try to find f plus g of x. And I would like you to also look at f over g of x. And then I'd like for you to think about the domain. So now would be a good time for you to pause the video and try to compute these. Alright, hopefully you've unpaused and have actually gotten the same things. If we look at f plus g of x, it's really like taking the function f of x and adding it to the function g of x. We know f of x was the square root of x, and g of x is x, so we'd have the square root of x plus x. If you haven't thought about the domain piece, let's do that right now. So when we look at the domain, when we look at the domain of g of x, just the x term, that's all real numbers. But we have some problems for f of x. So when we look at the domain is really going to mean from the square root of x, because we know that we can take the square root of 0 and we can take the square root of positive numbers, but we can't take the square root of negative numbers and get a real number. So again, we're going to look at when x is greater than or equal to 0. And we could use that in interval, or we could write that in interval notation. That would go from 0 to infinity. We include 0, which is why we have that square bracket. When we look at the second function, this is really like looking at f of x over g of x. So we know f of x, again, is the square root of x, and g of x is equal to x. Now, when we look to find our domain for this piece, we have to actually consider both a little bit more than we did last time. The square root of x still causes a problem, right? So we still have values when x is greater than or equal to 0. But the denominator says that x can't be equal to 0 because we don't want to divide by 0. So here our domain is from 0 to infinity, but we don't get to include 0 this time. Now that you're hopefully feeling comfortable with adding, subtracting, multiplying, or dividing functions, let's look at composition of functions. Alright, so composition of functions. We're going to look at this in two different ways. So we're going to start just kind of thinking about what it means graphically. So typically we start with our input values, or our x. And what we can do is we can say, alright, input those into a function. We'll call that g of x. So here's our bubble. G of x refers to these y values. And we can apply our function f. And we end up at the very end with f evaluated at g of x. And the idea is when we start at x and go all the way to this last bubble, that this is what we call f composed with g of x. Or our composition of functions. So when we look at composition of functions, we can look at f composed with g, it is not fog, of x. And what this really means is f gets evaluated at g of x. So we evaluate g at the function g at x first, and then take that y value and plug it into the function f. So the y value right here becomes an input, and then we get another y value. We can also have it the other way, so we could have g composed with f of x, and this is like taking g and evaluating the input as f of x. So we take g and evaluate it at f of x. So we input the x into our function f and then input that into g. These are not products. They don't mean to multiply. So that's one important thing to be aware of and to recognize. So we'll look at some examples. We're going to start with some examples that are maybe a little bit weirder, and then we'll move into some more typical ones. So our first example that we are going to look at is we are going to do some composition with sets. And we are going to consider the set H, which is the ordered pairs 2, 0, 4, 0, and 6, 8, and the set. And then the set J, which is the set of ordered pairs 0, 7, and 6, 0. And then we can close off the set. So I can ask us to find J composed with H, and then state the domain. Okay, so that means J composed with H. That's like taking the function J and using the input h of x. And one thing that I just will say is you'll see me often use a square bracket instead of these open brackets. I use that sometimes because I think it's visually a little bit easier to see what we need to do first. They mean exactly the same thing. You can sort of choose your preference. So, if we're going to do this, I think it's somewhat helpful to make a table. So what we're going to have to do is take our x values, we're going to have to put them into H, and we'll get a y value. And then we'll think about taking that second column and using those as inputs in the function J. Okay, so if we want to look at the x values that go into H, we're going to look at the first coordinates with H. So notice that we'd have 2, we'd have 4, and we'd have 6. So x could be 2, 4, or 6. Okay, if x is 2, then we want to think about x is 2, we put it in the function h, it spits out what y value, and in this case it should be 0. So the question we want to ask is, can we evaluate j of 0? What happens is if we use 0 as an input in the function j? Well, that's right here. If the input is 0, then this spits out the number 7. Okay, if x is 4, we're going to go back to good old h. If x is 4, it gives us the y value of 0. And then evaluate j at 0, again we get 7. And then last but not least, if we evaluate h when x is 6, we get a y value of 8. So we want to know, can we evaluate j of 8? Well, if we go and look at j, notice that our only input values were 0 and 6. So this one doesn't exist. So even though we can input 6 into h, we can't take that y value and plug it into j. So if we want to talk about the domain for this composition, j composed with h of x, we said we could plug in what values and get a y value back. So we're going to look here and look and see where we got a value in the last column. So here we can plug in 2. We can also plug in 4. We can't necessarily plug anything in between, which is why I'm using the squiggly bracket instead of interval notation. Now we can look at some examples of equations and do composition if we wanted to evaluate. So instead of looking at weird sets with ordered pairs, we'll look at some equations. So we're looking at examples of equations being evaluated with composition. So for these, we are going to look at our specific functions, f of x, which is equal to the square root of x minus 1, and g of x, which is equal to 2x. So we'll start this by finding f composed with g of x. Oops, I'm sorry, of 5. Okay, what this really means is we're going to evaluate our function f after we've evaluated g at 5. So here we're going to start by finding g of 5 first. That is looking at 2 times 5, or 10. So instead of thinking of g of 5, we're really evaluating f at 10. So we're taking the square root of 10 minus 1, or the square root of 9, which we know to be 3. Another one that I'd like for us to look at is, let's look at g composed with f of 5 and see what happens. So here we look at g and we evaluate that at f of 5. So to start this, we will look at f evaluated at 5 first. So we take the square root of the quantity 5 minus 1, which is the square root of 4, which we know is 2. So we're really looking at the function g evaluated at 2. So that's 2 times 2, or 4. So one thing that I want you to be aware of, f composed with g of 5 and g composed with f of 5. Do you see that we got different values in the end? They don't always have to be the same. In fact, most of the time when you do composition, you do not get the same values. So that is something to be aware of. The next thing we want to think about is how how does composition affect the domain? So we are going to look at two different functions. Let's consider h of x, which is equal to the square root of x plus 3, and j of x, which is equal to 3x. So let's first find what h composed with j of x is. And that's a little bit too big. H composed with j of x. Okay, so this is like taking the function a, h, and evaluating it at j of x. J of x takes a function and multiplies the input by 3. So we want to evaluate h at 3x. H takes the input, which in this case is 3x, and then we'd add 3. H composed with j of x is the square root of the quantity 3x plus 3. So, now for the hard part, or the more challenging piece. For the domain. Okay, so certainly if x had any restrictions, that would be important to recognize. But our y values, once we evaluate into the function j, they must be in the domain of h. If you guys remember that picture, right, we started with our x values, and then we put them, in this case, let me make it relevant to the picture that we have drawn. So we're starting with our set of x values. We first applied the function j, and then we got these new y values we called j of x, and then we used those as inputs and plugged them into h. Okay, so again, if there are restrictions on x, that's something we'd want to be aware of. But then we want to think, are the y values that we get with j of x, can we input all of those into h? So the idea here is, when we look at h of x, back up here, right, we know that we can take the square root of 0 and we can take the square root of any positive number. So if we were to look at just the domain of h of x, we would look at when x plus 3 is greater than or equal to 0 and solve for x. So we'd get that x needs to be greater than or equal to negative 3. Okay, that means any x value, or any value of j of x, any value of j of x needs to be greater than or equal to 3. Because the idea is we weren't really just looking at h of x, we were looking at this j of x. Okay, and what did j of x represent? It was really when 3x. So we want to know when 3x is greater than or equal to negative 3. We can divide each side by 3, and we'd get values of x that are greater than 1. So this tells us the domain for the composition. If you wanted to use interval notation, you'd go from -1 to infinity. And we use a soft bracket at infinity. Okay, so some of you might be thinking, well, it seems like I should be able to pick some other values. Okay, if we looked at -2, consider x equals -2. So we would first take x and plug it into j. j of -2, that's 3 times -2, or -6. Can we evaluate h of -6? Well, if we tried to, we're going to get a negative square root, and that's not defined over the real numbers. So hopefully this clarifies a little bit with the domain. I would also like for you to try j composed with h of x. and think about the domain there. Okay, so I would like you to find J composed with H of X and state the domain. We will talk about this in class, so I would like everyone to have tried it prior to coming into class. Alright, last but not least, I would like us to look at just a couple more examples. I would like us to write a function as a composition. So we're going to decompose the functions. Okay, so here's what I want you to know. We are going to look at, or you're going to be given 3 functions. So we can look at f, which is equal to the square root of x. We can look at g of x, which is equal to x minus 3. And then we can look at h of x, which is equal to 2x. And this is really f of x. So, here's what we're going to look at. Capital F of x. This is the square root of x minus 3. Now, some of you might look at that and have a hard time seeing how we can rewrite this. But do you guys notice that there's an x minus 3? That's what we said is g of x. And if you think about it, we're trying to plug g of x into the square root function. So we can think of this as taking the little function f composed with g of x, because we would evaluate g at x, which would give us this x minus 3, and then to take the square root, that's applying the function f next. If I gave you something like 2 times the square root of x minus 3, we could call this one k of x. So if we look at this, you could start again by thinking about noticing that x minus 3 is the same as g of x. And if you think about what we do next, we're going to have to think about applying h and f because there's a 2 and there's a square root. So which one would we probably want to do first? Well, my claim is that we want to think about applying the square root first, which is looking at our function f. And then we want to think about, after we've applied the square root, you want to think about multiplying that by 2. So my claim is that this is equal to h composed with f composed with g of x. Notice for this triple composition, this is saying take h and evaluate it at f, which we evaluate at g of x. Okay, so we'd start working with g evaluated at x, we'd plug that into f, and then we'd plug that into h.